Section 7.2 of your textbook covers the substitution method for solving a system of equations. Remember that a system of equations is a set of two or more equations that are to be solved simultaneously, and that a solution of the system is also a solution of every individual equation in the system. There are three main methods for solving systems of equations. We've already discussed the first method, which is graphing. The second and third methods are both algebraic methods that do not require drawing a graph. Also remember that although all three of these methods can be applied to other types of systems, we will be focusing primarily on systems of two linear equations. So to solve a system of two linear equations by substitution, there are four steps. First, isolate one variable in one of the equations. Second, in the other equation, substitute the equivalent expression for that variable. Third, solve the resulting equation to find the value of one variable. And fourth, substitute this value into one of the equations to find the value of the other variable. Let's look at an example to see those four steps in action. Our system contains two equations. We'll call the first equation x plus 3y equals 1. We'll call that equation 1 for easy reference. And then y equals 2x plus 5. We'll call that equation 2. Notice that equation 2 already has y isolated, so we're finished with step 1 of our substitution method. We'll go right to step 2 and substitute for that variable in equation 1. Since y is equivalent to the expression 2x plus 5, we can rewrite equation 1 as follows. X plus 3 times the quantity 2x plus 5 equals 1. Now we can solve that equation by applying the distributive property. X plus 6x plus 15 equals 1. Combining like terms, 7x plus 15 equals 1. And then isolating the variable first by subtracting 15 on both sides. 7x equals negative 14. And then dividing by 7 on both sides to obtain x equals negative 2. So we've finished step 3. Now we go to step 4. We'll substitute for x. We'll substitute negative 2 into equation 2. So y equals 2 times negative 2 plus 5, which means that y equals 1. So the ordered pair, that is the solution of the system, is negative 2, 1. And we have 1 point in our solution set. This means that if we were to draw a graph of these two equations, we would see two lines that intersect at the point negative 2, 1. Let's look at 4 more examples, gradually increasing in difficulty, solving each system and writing the solution set. First example, x equals 9y minus 4 is equation 1, and 7y minus x equals 10 is equation 2. Notice in this case, equation 1 has x isolated, so we will substitute from equation 1 into equation 2. Rewriting equation 2, 7y minus the quantity 9y minus 4 equals 10. We can solve this equation for y. And obtain y equals negative 3. Now we can go back to equation 1 and substitute negative 3 in place of y. To obtain x equals negative 31. Therefore, our solution is the ordered pair negative 31, negative 3. Again, 1 point in our solution set, so we have intersecting lines. Moving to the second example. Equation 1 is 6x minus 2y equals 16. Equation 2 is 5x plus y equals 8. In this case, neither variable is isolated in either of the two equations, so we need to isolate one of the variables. Equation 2 would be the easiest if we isolate y by subtracting 5x on both sides. Now that we've rewritten equation 2, we can substitute equation 2 into equation 1. So 6x minus 2 times the quantity, negative 5x plus 8 equals 16. And we'll solve this equation for x. To obtain x equals 2. Now going back to equation 2, which remember we rewrote as y equals negative 5x plus 8. We can replace x with 2 to obtain y equals negative 2. So the solution to our system is the ordered pair 2, negative 2. Once again, we have intersecting lines, in this case intersecting at the point 2, negative 2. You may recall, however, that there are two other possibilities for systems of two linear equations. Besides intersecting lines, you can have two equations that represent parallel lines, which would indicate that there is no solution for the system. Or you can have two equations that are equivalent equations and therefore have the same graph, meaning that there's an infinite number of solutions for the system. So let's look at two examples that show how the substitution method would lead you to one of those conclusions. In example number 3, equation 1 says 2x plus 4y equals 8, and equation 2 says 3x plus 6y equals 9. We need to isolate one of the variables in one of the equations. In this case, we will isolate x in equation 2. First, subtract 6y on both sides. Then divide by 3 on both sides, being careful to divide each term on the right-hand side by 3. So equation 2 now states x equals negative 2y plus 3. We can substitute into equation 1, replacing x with the equivalent expression negative 2y plus 3. Now we will solve for y in equation 1. First, applying the distributive property, and then combining like terms, we obtain the equation 6 equals 8. This is a false equation, indicating that there are no solutions to our system. The solution set is the empty set, and the graph of these two lines would represent two parallel lines. Finally, example 4, equation 1 is x equals y plus 7. Equation 2 is 3y equals 3x minus 21. Since x is isolated in equation 1, we will substitute into equation 2 to obtain 3y equals 3 times the quantity y plus 7 minus 21. Applying the distributive property, combining like terms, and subtracting 3y on both sides, we obtain the equation 0 equals 0. This is an equation that's always true, indicating that we have two equivalent equations in our system. This means the solution set for the system would be all ordered pairs that satisfy these two equations. We indicate that using set builder notation, a set of all ordered pairs xy such that x equals y plus 7. The graph, since these two equations are equivalent, would be one single line, and all the points on that line satisfy each equation individually and also satisfy the system. So we have infinite solutions.